Hey guys, hope you are doing well. I am currently in Singapore. I was planning to go out, but it started raining heavily, so I thought I'm gonna make a video. And today's video is gonna be very exciting. We will not be covering any recent AI topics or any AI agentic models, but we'll be focused on the core concepts. So, this generally gets asked in interviews quite a lot, especially during the machine learning system design interview. You guys might have guessed it already. We are talking about recommendation systems here. And yes, you are right. We have covered this topic earlier as well. But today's session will be a little different. It will be our go to guide for recommendation systems. So, we will talk about the basics of recommendation systems. Then, we will dive into this complex topic of building a large scale recommendation system. So we'll look at this framework from NVIDIA called NVIDIA Merlin. It has been used quite a lot in the industry now. So we'll cover different aspects of it. This include your feature engineering, your model development, model deployment, and model training. The recommender system domain is complex and there are diverse set of problems, use cases, data set, and model architecture. Hopefully by the end of this video, you will have a better understanding of this domain. A recommender model is just a standalone component. It could be a rule based algorithm or a machine learning algorithm. It generates a set of candidate recommendations based on user input or historical data. While the model itself can do code prediction tasks like estimating relevance or similarity, to get the final recommendation, you need a full end to end system, and this is called RACSys or recommendation system. It has multiple stages, as we discussed earlier: candidate generation, filtering, ranking, post processing, etc. Together, these components work in tandem to deliver personalized, relevant, actionable recommendations to users. Ranking models are arguably the most common and widely used type of model in recommender systems. A ranking model is designed to predict a particular target signal that indicates user preference or engagement. Common targets could be your rating a user might give to an item, or probability that a user will click on recommended item. So this can be used in many places like Amazon, where you click on an item to buy something, or click on an ad. Click through rate prediction is a common application of ranking models. So in the example above, you see it contains a data set used in training such models. So you will have like a user ID, user age, item ID, along with a binary target level click, which captures whether the user interacted with the item if or not. If explicitly negative interactions are not available, then negative sampling techniques are used to synthesize them for training. So it shows a sample model architecture in the second figure. Input features are embedded or transformed, concatenated, and passed through a multi-level perceptron, which consists of multiple fully connected layers. The architecture is commonly used for learning complex feature interactions and relevance scoring. So when it comes to Merlin, Merlin models offer implementation of popular neural network based architecture including multi-layer perceptron, neural collaborative filtering, deep learning recommendation model by Facebook, deep and cross network by Google, wide and deep also by Google. These models are implemented with a TensorFlow backend. So we'll do an example here for the ranking model, and then you will get on NVIDIA Merlin GitHub project. So if you go here, you can see that they provide you some Jupyter notebooks that help you build an end-to-end recommendation system with NVIDIA Merlin. There are a lot of projects available here or examples. The movie lens example, Pretio, AWS SageMaker, but we are mostly focused on this part. So they also provide a set of containers. So if you come here, you can actually download the containers for Merlin. So if you select here Merlin, you can see some of these containers. So we'll use Merlin TensorFlow. PyTorch training is also there. Then Merlin UCTR, PyTorch interface, and so on. So for us, I'm gonna go ahead and select this um, Merlin for TensorFlow, and I'm gonna run this command. So what this does is it pulls the training container with the following command: And now if I go to my terminal here, on my terminal now, if you want to see all the Docker images on my machine, I can do Docker images, and you will see I have UCTR, Merlin UCTR, and Merlin TensorFlow. We only care about Merlin TensorFlow, so we will be using that image. So just to be just to keep you guys aware, the image is huge. So in this case you can see that it is 30 GB, this one is 14 GB, this one is 17 GB, so they're gonna take time. So now if I do the run command, which is your docker run, so this is my docker run command. So you see here, this is the repo, so you don't have to worry about, though it says UCTR, but we don't have to worry about it. The image that I'm using is this. So NVCR, this is the Docker hub, and then I'm gonna use Merlin TensorFlow. So I'm gonna run this. So now I'm logged into the image. So this is the Docker image that I am in. Great. What we need to do here is to start the Jupyter Lab server so that we can run our Jupyter notebook. I'm using AWS Cloud. So what I need to do here to access Jupyter Lab notebook locally is to do port forwarding. So port forwarding is nothing but it's a technique where you can redirect communication requests from one address and port number to your local or any other address. So in this case, I'm gonna redirect from EC2 to my local. So you'll see that I should be able to access this whole Jupyter notebook using the local host server. So let's get that started. So I'm gonna do Jupyter Lab and run this command. So awesome. So the Jupyter Lab server is now running, and what I need to do is to access this locally using this address. This is my Jupyter Lab notebook. If you see here, you'll see they structured all the projects that are there. I think we need to use the Merlin project probably. Examples here. There is a scaling Cretio example I can see, which is, and then there is NVIDIA Merlin UCTR. Downloaded the wrong project. Actually, we need to download this specific project here, which is called NVIDIA Merlin models. So this project has a lot more Jupyter notebooks and focused on ranking models. So let's take a look at that. So here we are using the Merlin TensorFlow container. So the first step is to import all the libraries. So I'm going to click on this and import all the libraries. The main library here to notice is NVTabular. It's a feature engineering library which NVIDIA provides for high performance feature engineering for large scale recommendation models. So I just installed it and then get all the data. So here we are using Parquet files for the click-through rate prediction dataset. So this is the Alibaba CCP dataset. It's called Alibaba Click and Prediction dataset. And if you go here, you can get the dataset in this link. Anyways, so I downloaded the dataset, created a data folder, and put all the values there, all the data there, and then we're gonna generate these folders with the train path, validation path, and output path. So one thing that you need to notice that there are some categorical variables. So there could be multiple techniques for categorical variables. You can use one-hot encoding or label encoding, but here they are using target encoding. So we'll use target encoding. So what it does is basically converts your categorical variables into numerical values based on the target variable. So in this case, the target variable is click, right? Whether the user has clicked. And if let's say if a feature is user country, US, let's say if they have clicked, the target variable is 1 for 5 of the values, and then 3 for 3 of, or rest 5 of the values, the value is 0. So in this case, the average will be 0.5, and thus the user country target encoding will become 0.5. Similarly, let's say if UK is the variable, and then all the users in UK has clicked, then the target encoding value will become 1. So that's the idea here. So you kind of use the mean of the target variable. So I'm gonna run this here. So you can see that they are doing a target encoding here, and then and then calling the fit transform. So NV tabular exported the schema file for our process dataset. It's a protobuf text file that contains feature metadata, including statistics about features such as cardinality, min value, and max value. And then I'm gonna run this again. Click, and then you can see the column name. So these are the column names that they have used: user ID, click, user item categories, user item shops. Some of these fields from the data set, and the target encoding. So these are all categorical features, so you convert it into target encoded values. First model that we'll be using is neural collaborative filtering. It is a very well known paper published in 2017. You can find the link of the paper in the description. It's based on matrix factorization. If you are not familiar with matrix factorization, the matrix factorization is a decomposition technique where you decompose a matrix M into smaller matrices such that the multiplication of those matrices can ultimately result in approximation of M again. So this kind of breaks down the matrix into smaller parts, and you can achieve this using SVD or linear LU. So you can consider NCF as a framework that supports multiple models. It supports your NeuroMF, your generalized matrix factorization, or multi-layer perceptrons. As you can see on the screen, there is the architecture of this model. So you have the GMF layer and MLP layers, and then NCF feeds categorical features into embedding layers, concate the embedding output, and add multiple hidden layers via its MLP layer tower as shown in the figure. So here you can see that on the right side there are multiple MLP layers which are hidden. Generalized matrix factorization and MLP uses separate user and item embeddings, and then the output of their interaction from GMF layer and MLP layer are concatenated and fed to the final neural matrix factorization layer. So this is the architecture of this model. Code here. So we will load the NCF model. So we are using the Merlin library. So it has the MCF model already integrated. So I'm just gonna pass this. You can see that I passed the dimension of the embedding vector, multi-layer perceptron block, and the prediction task of binary, which is 1 or 0. And I'm gonna run this here. So my model is ready. This is running on TensorFlow. So you can load the keras here. So now we are compiling the model and then fitting the model. So this may take some time. So here we have the results. You can see it had 43 epochs and it completed the run. This is the validation batch loss. And let's save our accuracy results. So we're gonna save it in the results section and save results. Evaluate how our model did. So we're gonna run the evaluate function here, and this is the loss that we got. Probably it's a binary cross entropy loss here. Area under curve is around 0.50, regularization loss is 0, and then batch loss is 0.75. So honestly, the metrics looks terrible. Just to give you more context here, the loss of 6.6931 means that the average loss over the data set, likely binary cross entropy as I mentioned earlier, AUC is 0.50. So this is very, very low. 0.5 means that the model is guessing at best. So it's not really predicting anything with just a random return. Regularization loss of 0.0 means that, so regularization loss is the penalty term added to avoid cross-fitting, overfitting. And here it is 0.0 or 0.0. So that means you are not applying any regularization, or we are not applying any regularization. Loss of batch is 0.6937, likely the loss from the current batch. It's slightly higher than the overall loss cases. If I ask you how do you debug this now, considering that we have such a terrible loss or area under curve, I would say you can train longer, so maybe add more epochs here. We need to cross check the embeddings. I have a feeling that the user item embedding is not actually working. Model that we can try for ranking is the wide and deep model. There is a small video from Google around wide and deep model. Let's hear from them first.
Wide and deep learning combines the power of memorization and generalization, and it does that by jointly training wide linear models and deep neural networks. We're sharing a research paper about it and also the implementation with an easy-to-use API in TensorFlow. So you might wonder what wide and deep learning is good for. Wide and deep learning is useful for generic large-scale regression and classification problems with sparse inputs, things like recommendation systems, search, and ranking problems. Now, imagine you wanted to build a search engine for food. Given a query, you want to recommend the items that your users will like the most. Using wide linear models, you can actually use a wide set of cross-product feature transformations to memorize specific feature combinations. An example would be when the user say the query fried chicken, your model might memorize that chicken and waffles is more relevant than chicken fried rice. But one limitation is that it's actually hard to generalize to previously unseen combinations without manual feature engineering. So instead, using deep neural networks, you can now generalize better through lower dimension embeddings. For example, your model might learn to recommend burgers given the query fried chicken because they're similar types of food. However, sometimes memorizing specific combinations as rules and exceptions is very important. You know, when people ask for iced decaf latte, you don't really want to overgeneralize and give them hot latte, no matter how close they are in the embedding space. So by jointly training wide and deep models, we actually allow them to complement each other's strengths and weaknesses.
Implement this now. So there are two parts here, wide and deep. For the wide part, we will need categorical features, and for the deep part, both the features are fine. So what we need to do is first identify the categorical features from the schema, and then do category encoding or one-hot encoding here. So linear models not able to compute feature interactions. So to give the wide part more power, we perform feature interactions. Although this approach leads to high cardinality resulting in features, so typically we apply the hashing trick to limit the resulting cardinality. So let's get this done with the hashing cardinality. So we did one-hot encoding. You might have noticed that we set output of one-hot and cross features to be sparse tensor. Yes, as only few values are ones and the large majority of these are zeros. This is because negative sampling. This saves a lot of memory. Now we have categorical features which have multiple values on the same sample data. You can use output mode is equal to multi-hot for both this. So I'm gonna run this. Now let's look at the deep part, which is a multi-layer perceptron. Now we're gonna call this. So we have a deep part model here defined, and we have this feature is crossing wide processing block. Now we need to combine them. So we're gonna run this model. The model has completed the run. You can see it has finished the epochs. Now save the results. So it has saved the results. Let's look at the evaluation matrix. Okay, again, this is again a very terrible matrix. Probably it has something to do with the labeling of the data. Probably we are not using it correctly, but anyways, that's beyond the scope of this. So here you can see the model has completed running. So there is a deep learning recommendation model that you can use with the Merlin TensorFlow. We are not gonna use this. It's very simple. You just need to replace the previous model with DLRM model. The architecture is somewhat like this. This was released by Facebook in 2019, so it's pretty old, so I'm just gonna skip it. The model here is the DCN V2, which is also called as Deep and Cross Network V2. So this is mostly for tabular data, and it's an improvement over the original paper. So it has two branches main, the deep network and cross network. So cross network is mostly for explicit high order feature interactions. So cross layer follows here, you can see. So this also has like mix. So if you see here in parallel, you can also have it in parallel. And this also has like mixture of experts. Each expert learns a different set of interaction and low rank factorization. And deep neural network here is more like a MLP, and it learns implicit features. And then you can kind of concatenate the output of cross and deep neural network. Anyways, running this is also very simple. Just call this model legacy grad or add a grad and then save results and then evaluate. Ranking model part of the project, but let's try to understand how feature engineering works and how Merlin as a framework helps us optimize some of the processing on GPUs and CPUs. So what exactly is Merlin? Merlin is an open source framework for building large scale recommendation systems. It is designed to support an end to end pipeline from training to deployment on CPU and GPUs. TensorFlow already integrates. PyTorch is also integratable now. I think there is Docker image available for PyTorch. And then it has two main components. Merlin models, the library that we used, where we had the DCN models and the few other models. NVTabular is a feature engineering and processing library for tabular data that is designed to easily manipulate terabytes and scale of data. So this is huge. It provides high-level abstraction to simplify code and accelerate computation on the GPU. So it uses Rapid's Dusk's CUDA data frame library under the hood. And integration of NVTabular and Merlin models. So you see there is a feature engineering part with NVTabular, then you generate the schema files and then you pass it to the model training. So you remember that we were using the DCN model, which requires you to have categorical features converted. For that we generated the schema file, and that's what is referring here. So NVTabular will output a schema file describing the dataset structure. The schema file contains columns, statics, metadata all collected by NVTabular. Here are some of the examples of such metadata computed by NVTabular processing. Important operations where you can use an NVTabular. So categorify and normalize. Categorify means that you have the categorical columns and you transform them into continuous integers for embedding layers. The columns that are processed by this operation save in the schema. Its cardinality and also tagged as categorical. Normalize is standardization to normalize continuous features. The mean and standard deviation of the columns are saved to the schema. The user can also define their own tags. So let's import all the necessary packages to run this. So I'm going to import this. Anyways, so just coming back to this, understanding the schema file. So this is how the schema file, and NVTabular process the data. It will process the schema to a file or a disk. You can access this schema from the Merlin dataset class. So this is the schema. All the IDs, so user ID, movie ID, title, genre, gender, age, and so on. And here you have the schema. What kind of data type it is it a list, is it dragged, and few other things. And then these are encoded categorical features which we talked about earlier. You can also select the features by name. Alternatively, you can select them by tag as well, so you can get all those features. This is how like the feature engineering works. So it's basically acting as a feature store. The schema is a great interface between feature engineering and modeling libraries, describing the available features as their metadata statistics. It makes it easy to build generic model definitions, as the feature names and types are automatically inferred from schema. This means that when the data set changes, you don't need to change the modeling code. Integrated pipeline with NVIDIA and Merlin models. Download and prepare the data. So it took me a while and I was able to generate the data. We process the data set and split it into training and validation. So this is the movie lens data set. It's done. Now we used NVIDIA to define pre-processing and feature engineering. So this is how you do it. So the features column operation 1, operation 2, we need to perform the following step. Categorify user ID and movie ID that the values are continuous integers from. Transform the rating column to a binary target by using the threshold value 3. Add tags with this. Category 5 will transform the categorical columns into continuous integers for embedding layers, as we discussed earlier. Coming back to the modeling part, so in a large recommended system, the size of item catalog might be in millions or even billions. At such scale, we generally follow a two-stage pipeline process where there is a faster candidate retrieval model that quickly extracts thousands of items from a set of, let's say, million items, and then there is a more powerful ranking model which takes these thousand features and kind of give you a top k item. The best way to implement retrieval model is through two tower architecture. So you can think of them as two independent neural networks. One is for the user tower and the other one for item tower. User tower process user specific information like user ID, historical behavior, demographics, time of day, and outputs a dense user embedding vector. Whereas the item tower process item specific features like item ID, category, metadata, and outputs a dense item embedding vector. Each tower is trained independently. Only its successive features allows it the embedding to be generated offline for items and online for users. The final retrieval score between a user and an item is computed via the dot product. Optionally, you can use cosine similarity to normalize both vectors. The design ensures that the computationally expensive interaction between user and item representation is deferred to the final step. I found this video from Eugene Yan super helpful in explaining the concept of retrieval and ranking. So I'm gonna give a small part of it and you can get the full video from the link in description. Let's check it out.
So we have the embedding model, we have the approximate nearest neighbors index, we have the feature store, and we have the ranking model. And these are the artifacts that we will use in the online. So online, what happens when a request comes in? So let's say a request comes in, hey, I am now looking at the movie for, I don't know, The Matrix. The matrix becomes a vector of 32 dimensions or 64 dimensions, and we retrieve the top 1,000 candidates that are most similar to the matrix. Okay, we have Matrix 2, Matrix 3, I don't know, other sci-fi movies. So from this 1,000 candidates, we're going to add features to the candidates, right? Add features to the matrix, like what category it is, which year did it come out in, I don't know, box office sales, how many users liked it, how many people watch it in the past 24 hours, it could be trending. So we add features to it. We also add features to the user, and then we rank the top K candidates, right? So given 1,000 candidates, and maybe on a homepage of Netflix, you can only probably show 20 or 50. You rank them, and which are the 20 or 50 topmost, and we get the results. So this is overall how it looks like in a very abstract, simplified view.
We are back here on the coding side. So as usual, we will import the NVIDIA library for data pre-processing and feature engineering, and we're gonna run this code. Hopefully, I will not face any error because I was getting like out of memory CUDA exception before. Okay, let's do some feature engineering, guys. Let's go for it. So you see here, I created. So this was already done in the ranking model as well. So nothing changing here. Okay, so we have a training data set, testing data set. So we can drop the target column since in this example we'll only use positive interactions and then generate negative interactions via negative sampling. Okay, so now let's create the dataset objects and then we will define output paths. So this is the Merlin terminology. They have a dataset class that you can use, and then you created this here, and now you're gonna do categorify. So categorify is a property of NVTabular. So you are converting these categorical variables to linear, and this is how it can be done. So you have these. So basically, you are generating the embeddings here. So user ID and item ID, and then item features, user features are both added. So it's gonna be a two-tier architecture, two-tower architecture, and you're gonna run transform. So two-tower model here you can see with Merlin. So we have a separate user features and separate item features, and this is how the two-tower architecture look like. We already have looked at it, so we're not gonna dive too much into the architecture. Just focus on the code. So get the training. Next, the next step is to generate the schema. So this is where we pass the select by tags, item ID, user ID. These are the features that we want to transform or generate embeddings for. So it's gonna convert them into schema. If you want to look at the schema, this is how it looks like. So you have the user ID, the data type, tags, list, ragged, and some of these properties. So this is how these are all the features for this user or for this use case. And then we have no empty negative sampling. Many data sets for recommended system contain implicit feedback with logs of user interactions. To be able to learn from implicit feedback, you use the general assumption that the interactive items are more relevant for the user than non-interactive items. So basically, this we already discussed, but just want to mention that you consider those items that has not been clicked as non-interactive items, and they are negative kind of. Building the model. So let's try to build the two-tier model, two-tower model. So tower dimensions is 64, user schema, and then user inputs from the user schema, and then encoder. So you kind of encode this as and then item schema. So you do the same thing for two tower. Model.compile and model.fit. So here the code is running now. So it's for two epochs. Batch size is big, so I'm worried that it might give out of memory, but let's see. But the epochs are only two, so should not be big deal. Okay, perfect. So the model has been trained and it has fit. Now let's try to evaluate the metrics. Let's try to get this working. Just unique rows by features. This top k. Now we'll get the top k candidates. That's what the retriever model does. It basically gives you the top k elements. In this case, k is 20, so it's gonna run that model.top k encoder. So now here it's basically giving you top k. And now let's run this again for the metrics. These retrieval evaluation metrics suggest low performance. So loss of 0.40, this is overall training loss, which by itself doesn't say much, but it's relatively low. Generally, if you have low training loss, then it's a good sign depending on your target and loss function. But in this case, it's not really meaning much. Recall at 10 is giving you 0.08. That means out of all relevant items, only 8.4% are being retrieved in top k results. Low recall, meaning many relevant items are being missed. Generally, the good recall value here could be around 0.2 to 0.3 depending on the use case, but that means the model is not doing well. MRR at 10, the mean reciprocal rank is 0.0339. Measures how early the first relevant item appears in the top k, and 0.0339 means that the relevant items are far often down the list or missing entry. Generally, it should be around 1 as good value, closer to 1. NDCG at 10 is 0.0456. Considered not just relevance but ranking quality. Very low. Strong models often have 0.2 to 0.3, which is again terrible in this case. MEP at 10, similar to MRR but average precision across all relevant document, not just the first. Again, very low. That means the model isn't retrieving most of the relevant items. precision at 10 is 0.0084. That means out of the top 10 results, less than 1% are relevant, which is crazy, like how bad we have done. This is extremely low, indicating a noisy or poor retrieval result. Regularization loss is 0.00. No penalty from regularization. That means that the model has not started regularization. Loss batch is 0.4520, slightly higher than the overall loss, may indicate some batches were still poorly learned. So that means that the model is performing poorly in actual retriever. The metrics are very low. Another important class of models in Rexway system is sequential and session based models. Let's try to understand what those are. Any real world scenarios, user interact with items in a specific sequence. So let's say you are reading a news of a plane crash. So once that happen, you will probably try to read or watch other kind of related stories around that. So these are dependent on that specific context. These interactions are not independent. Instead, each action may depend on the what the user did just before. To leverage this sequential behavior, one approach is to preserve the chronological order of user interactions when training your ranking or retrieval model. Specifically during training, the data is sorted by users and timestamps so that the model process interactions in the same order they happen. This allows the model to capture temporal dependencies, what users are likely to do next based on the recent behavior. Common models used in this setting includes RNNs, GRUs, transformers, other architecture that can model sequence and sessions. So very well known architecture transformer kind of keep context of what how relevant the previous sequence has been to this one. So this is an architecture that you can use here for these sequential models. By not shuffling the data, the model is updated with each new interaction in order it is occurred. It can learn from the most recent user behavior, which is often more predictive of future actions. For example, if a user watches action movies followed by a thriller, the model learns that they may prefer thriller next and it adjusts accordingly. In many systems, models are not updated real time. There is typically a delay between the new user interaction are logged and when the model is retrained. As a result, the model's understanding of a user may be outdated, especially for high dynamic or short term preferences. To overcome this, you can actually do the current user session of user interaction, often without needing long term history. They can be trained to capture short term intent effectively and may be used in combination with the long term user embeddings. Yeah, I think that covers the concept of recommendation systems and different approaches that you can take along with NVIDIA Merlin implementation. Let me know in the comments how did you find the video. Otherwise, I will see you in the next one.